Morning, sir. Shall we start, sir?
Yes, ma'am.
Yes, sir. Shall we start this?
Yeah, yes, please.
Thank you, sir.
அவர் பின் பண்ணியிருப்பார் வேற ஒன்று
Pin பண்ணுங்க.
ஸ்க்ரீன்ல
A warm and pleasant greetings to all the participants, those who have joined the second day first session for this 4 days national conference on contemporary mathematics and applications, organized by Postgraduate and Research Department of Mathematics, Dwarakadas Govardhan Das Vaishnav College, Chennai. Faith and prayers both are invisible, but they make impossible things possible. Let us begin our session by a prayer song seeking the blessings of Lord Almighty, followed by Tamil Thai Valthu.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य नेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
Mathematics is the art of giving the same name to different things. It gives me an immense pleasure to welcome our eminent speaker, Dr. R. Sundareswaran, Associate Professor, Department of Mathematics, SSN Engineering College, to enlighten us today by his talk on secure equitability in graphs. Sir completed his BSc from Tyagaraja College of Arts and Science, affiliated to Madurai Kamaraj University, Madurai, MSc and MPhil Mathematics in Saraswati Narayanan College, affiliated to Madurai Kamaraj University, Madurai. Sir has more than 15 years of teaching experience and 5 years experience as a full-time research fellow, and worked as a senior research fellow in the National Center for Advanced Research in Discrete Mathematics, sponsored by the Department of Science and Technology, New Delhi. His area of specialization is vulnerability parameters in graphs, and interested in research areas as fuzzy graphs, combinatorics, discrete mathematics. And Sir did his PhD as a part of 3-year research project entitled Domination Integrity in Graphs, funded by Department of Science and Technology, Government of India. At present, Sir is doing project as a principal investor on the title Analyzing Diabetic Neuropathy, a graph theoretic approach, funding agency SSN Trust. Sir has published more than 35 research papers in many national and international reputed PR and Scopus Index journals. To his credentials, Sir has received many awards as a reviewer for American Mathematical Reviews and also a referee for WSEAS journals and TWMS journals. He is a membership in professional bodies like Life Member Society for Reliability and Safety, Life Member Association of Discrete Mathematics and Applications. Sir has organized and delivered invited talks on many national and international conferences, workshops, and webinars. With this brief introduction, once again, I welcome you, sir. I hand over this session to sir.
Thank you so much, ma'am. Thank you so much for your nice introduction.
Thank you, sir.
Is it visible, ma'am? Can you see the screen?
Yes, sir. It's visible.
Yeah. So it's a very good morning to all. First of all, I extend my sincere thanks and pranams to Professor R. Venkatraman for having given this opportunity second time in the same institute. Especially thanks goes to my friend, my brother, Professor K. Venkatesh, and my beloved guide, Dr. V. Swaminathan. Without them, I cannot reach this stage. So whenever I give a talk, I should thank both Professor K. Venkatesh and my guide. So today I'm going to talk about secure equitability in graphs. So recently I have submitted this paper to Discrete Mathematics Applicable Analysis Journal. It is under review. So this work is combined with my guide, Professor V. Swaminathan, and my junior L. Muthu Subramanian. So these are the topics, these are the headings of my presentation. Introduction about the topic, then secure equitable dominating set, secure independent and equitable partition of a graph, secure equitable sets and secure equitable independent sets, then secure equitable independent complete graphs, and matrix formulation of secure equitable domination. These are the topics I am going to cover this 1 hour talk. So generally I start with the basics of graphs. So what is graph? Graphs are formulation for representing relationship among items. So relation between human social network or brain network or even in water network. Recently people are working in water distribution network. There is a journal called Journal of Hydroinformatics. This is a very high impact journal. Impact factor is 2.1 something. So there are more than 50 to 60 papers published based on graph theory. Especially there is a concept called centrality matrices in graphs. So they use centrality matrices. They identify what are the hubs, what are the blocks in water distribution network. So the papers published in that particular journal by only engineering people, especially civil engineering people, published more papers on that particular journal. You can go through it on Google, Journal of Hydroinformatics. Okay, I come back to this basic definition of graph. Graph is a pair of vertex set and edge set, a set of vertices which are denoted by capital V, vertex, the elements of the set V1, V2, Vn are the vertices of the graph. So like that, the element of the edge set is E1 to Em. Each edge EI is a pair of vertices Vj, Vi and Vk, or Vj, Vi, Vj. An edge connects the vertices Vi and Vj. So generally we classify into two types of graphs. Graphs can be directed or undirected. So throughout my topic, I'm going to consider only undirected graphs. So what is meant by open neighborhood of a vertex? It is denoted by a set. It's a collection of vertices which are adjacent with that vertex U in G, V of G. Then here I take only the neighbors of U, excluding U, U, I take other vertices, the neighboring of the vertices which are adjacent with U. A close neighborhood of U is something a little bit extra element. Just we include U also. So it is denoted by N close bracket, square bracket U, which is equal to N of U, union U, it's not intersection, it's union U. So the basic concepts which I have took from the book Graph Theory by Frank Harary. So this is a very famous definition. Most of you heard about this definition. Just I give a small introduction about this. What is my dominating set? A subset D of a vertex set V of G of a simple, finite and undirected graph G is called a dominating set of G if for any vertex in V minus D, there exists a vertex U in D such that U and V are adjacent. Then the smallest set is called dominating set. The cardinality of such a minimal dominating set is called domination number, which is denoted by small gamma of G. If the cardinality is maximum, then that is denoted by upper domination number, capital gamma of G. So based on the definition, we have a characterization theorem when a vertex belongs to that particular set. So a dominating set D of G is minimal. The word minimal is catchy. If it's minimal, if only if for any vertex in D, U in D, either U is an isolate of D, that is U is not adjacent with any vertex of D, or there is a vertex V in V minus D, which is adjacent with only U in D, which is nothing but private neighbor. The private neighbor of U is nothing but V, or U is an isolate vertex in induced D. So you construct a subset of a vertex set V of G, is denoted by D. Then a vertex has eligibility to be a part of that particular subset. There are only two cases: either the vertex is isolate inside D, or it has a private neighbor outside. These are the only two possibilities for a dominating set is said to be minimal. This theorem is called Worth's theorem. So we have a proof also. What is my irredundant set? A subset S satisfying the minimality condition of a dominating set is called an irredundant set. For a dominating set, this is either or. Either U is an isolate, or there exists a vertex V in V minus D which is adjacent with only U in D. Now I construct a set which is called irredundant set satisfying any of these two conditions. Satisfying minimality conditions of dominating set is called irredundant set. Like that, we calculate the cardinality of that particular maximal irredundant set, because here we take maximal, not minimal, maximal irredundant set. Depending upon the cardinality, if it is minimum, then the number is called irredundance number. If it is maximum, then it is called upper irredundance number. These are the notations for irredundance number: IR, small IR, and capital IR. So these are the direct results. A minimal dominating set of G is a maximal irredundant set, because minimal dominating set satisfying any two conditions, automatically it should be a maximal irredundant set. Similarly, maximal independent set. Independent set is nothing but a subset of vertex set in which every pair of vertices are not adjacent. All the vertices are isolates, then it is called totally isolate, then it is called maximal independent set, which is also a minimal dominating set. These are the two major theorems in domination theory, but I am not getting to that. So this is the definition of independent set: no two of which vertices are adjacent. Then the vertex set subset is called independent set. The cardinality of that particular set is called independence number. Maximum cardinality of an independent set is called independence number, which is denoted by beta naught of G. There are other notations In some papers, authors denote alpha, beta, something like. Here I take the notation beta naught of G. Throughout the topic, I'm going to mention beta naught of G is nothing but independence number. So if it is a maximal independent set, no proper subset of any other independent set. It does not contain any proper subset of any other independent. Then that is called maximal independent set. So set of vertices in G, which is said to be a independent dominating set, and then you combine both the things, the concept of independence and dominating. So we club to these two topics, then that set is called independent dominating set. There are many applications, plenty of applications for dominating set and independent dominating set. Recently, we have published an article, domination integrity, that is a different area, which is called vulnerability parameter. So under which we published an article based on electrical circuits, how we use the concept of dominating set as in application side. So the minimum cardinality of an independent set is denoted by small I of G, minimum independent dominating set. So there are different notations: small gamma, capital gamma, then beta naught, small IR, capital IR, and I of G. There is a relation among all these notations. This is an inequality chain. IR less than or equal to gamma, less than or equal to I of G, which is less than or equal to beta naught, which is less than or equal to capital gamma, which is less than or equal to capital IR. It's called dominating chain or domination chain. K.M. Dharmalingam has published many articles based on equitability concepts, equitable domination. So I will list out those definitions initially. Then I move to secure independent equitable concepts. A vertex U in V of G is said to be degree equitable with a vertex V in V of G if the degree difference between these two vertices is less than or equal to 1. That is, suppose you consider these are the two persons in a human relation network in an institute or in an industry. So the people, those who are knowing to U as well as V, the number of difference between the number of neighbors or number of friends of these two vertices should differ at most to 1. The degree of U is nothing but the vertices which are adjacent with U. Degree of V is nothing but the members which are adjacent with V. So the difference between these two number of neighbors is less than or equal to 1. Then these two vertices are, this vertex is said to be degree equitable with the vertex V. So we can collect degree equitable, but in general a regular graph, always all the vertices having the same degree, so it should be less than 1. Definitely it should be at 0 because the degree are equal. For example, complete graph, cycle, the degree difference is 0. So automatically every vertex is a degree equitable vertex. Based on this, Dharmalingam introduced a concept called equitable dominating set. Just see, combined equitable concept with the dominating set. So once you construct a dominating set, then we impose the condition. You take any two vertices, U in V, U in D and V in V minus D. The degree difference is less than or equal to 1, as well as they are adjacent. If they are adjacent, then we can talk about dominating set. If the degree of difference is less than or equal to 1, then they are degree equitable. So combine these two conditions, which is called equitable dominating set. Then you identify what is the minimality condition, what is the minimum cardinality of such a set, which is denoted by gamma E of G. So throughout the topic, I'm going to talk about this gamma E of G. If D is an equitable dominating set, then every superset of D is an equitable dominating set. If D is an equitable dominating set, then clearly any superset of D is an equitable dominating set. Then like what we have discussed in the earlier part, neighborhood, open neighborhood and closed neighborhood. Now I defined neighborhood in terms of equitability. You take a vertex in a vertex set, then equitable neighborhood of U is denoted by NE of U, which is nothing but V in V of G, V in N of U, as well as the degree difference between these two vertices U and V less than or equal to 1. If it is in the neighbor, then that is called open neighborhood. Here I imposed another condition, that is the degree difference at most difference at most less 1. Then the combine these two conditions along with a vertex set, then that is called equitable neighborhood. Similarly, equitable isolate. If this particular set is empty, then the particular vertex is called equitable isolate. Generally, in any set of isolates, This is basically equitable isolates. So set of all isolates, equitable isolates are denoted by IE. Throughout the topic, I'm going to denote IE is nothing but I collect all the vertices which are equitable isolates. Okay, that is whose equitable neighborhood is empty. Then that is called equitable isolate. What is my equitable degree of U? Degree of U is denoted by the cardinality of this particular set. How many vertices in this particular set? That is the vertex, the set of vertices satisfying these two conditions. Then the cardinality is called equitable degree of that particular vertex. I will show you an example in later stage. Then based on that, I have two notations. One is maximum and minimum equitable degrees. Maximum degree is maximum cardinality. Minimum degree is minimum cardinality, like what we have in ordinary degree concepts. Okay. Similarly, we extend the concept of degree equitable irredundant set based on the minimality condition. Here the minimality condition is n of U intersection is empty, that is, which is isolate, and the degree difference is greater than or equal to 2, which is nothing but equitable isolate. That is the first condition. Second condition, you take a vertex outside, then such that n of V intersection S is U, only U. That is, the private neighbor of U is V, or this is an additional condition. Additional condition. Apart from these two, we have this condition also. There is a vertex outside V minus S. Then n of V intersection S is U, and also the degree difference between these two less than or equal to 1. So in dominating set, we have only two conditions: private neighbor and isolate. Here we have equitable isolate and the condition of equitability, degree equitable difference. So there are three conditions for degree equitable irredundancy. This is also minimal conditions for minimality of equitable independent set, equitable dominating set. So later, Lakshman Raj continued this work, equitable domination and irredundance in graphs. They defined the other concepts also. He also introduced the concept of equitable coloring. A proper coloring is said to be equitable coloring if the cardinalities of any two color class differ by at most 1. Here I take color classes. You know what is coloring? So coloring is nothing but you are going to color each and every vertex such that no two vertices, adjacent vertices, receive the same color. Then you do the proper coloring with the minimum number of colors. That is called proper coloring. Is said to be equitable coloring. You take any two color classes whose cardinality of these two color classes differ at most 1. Then that is called equitable coloring. Then there is a paper published based on this. Okay. Then what is the equitability independent set? Equitability actually introduced by Professor E. Sambat Kumar. Degree equitable. Two vertices are said to be degree equitable if the absolute difference of their degrees is less than or equal to 1. Then they combined domination and introduced equitable domination and equitable redundancy, everything. Then there is a one paper which is published by Anita et al. Along with Professor Arumugam. They defined a degree equitable proper coloring and made an extensive study of this concept. You can download these papers from Google. Anyway, I will show you in my reference. So a subset S of V of G is called an equitably independent set if for any U in S, V not in equitable neighbor of U, for all V in S minus U. So in ordinary independent, we are talking about only adjacency, but here equitably independent set. So the particular vertex which is not a neighbor, equitable neighbor of that another vertex U. This is true for each and every vertex. Every pair of vertices satisfying this condition, then that is called equitable independent set. Generally, every independent set is an equitable independent set. There is a equitability independent set which are not independent. We have an example. For example, you take star graph K1, n. You take a single vertex, then there are n leaves, then which is an equitable independent set, but not as an independent set. Because in K1, n, the middle vertex having the maximum degree, n, the degree of the center vertex is n, whose leaves are pendant vertices, the degrees are 1. So all are equitably isolate. If they are adjacent, but they are equitably isolate. So that is a equitably independent set, but not independent set because they are adjacent. They are adjacent with the center vertex. So one way is true. Every independent set is an equitable independent set, but we cannot say that equitable independent sets are independent. Based on that, we construct, we can find the cardinality of such a maximal independent, equitable independent set, which is denoted by the minimum cardinality is small ie of G, and maximum cardinality of a maximal independent set is beta naught E of G. Then these are the direct observations. You can easily prove these results. Independence in the cardinality of maximum independent set is less than or greater than or equal to beta naught E of G. Similarly, for K1, n is n plus 1, but in K1, n, all the pendant vertices are in independent set, so n. So the difference is 1. Moreover, it's a hereditary property. A equitable independent set is hereditary. Then based on that, we can prove this theorem. You take a simple graph, maximal equitably independent set of G is a minimal equitable dominating set of G. This is from the theorem every maximal independent set is a minimal dominating set. Just we extend the same based on the equitability concept. Then we construct the chain also, gamma IE of G, beta naught of G, and capital gamma of G. Moreover, the difference between equitable independent dominating set and independent dominating set is equal to K. The difference between, we can construct a graph, connected graph, whose values IE of G and beta naught of G differs at most K, exactly K. So we take a path on 2K plus 3 vertices, U1 to U2K plus 3, then attach 2 pendant vertices at U2, U4, and only you add pendant vertices, 2 pendant vertices only in even vertices, even number of vertices. Then whose IE of G is 4K plus 1 and beta naught of G is 3K plus 1. So the difference between these two is K. This is an example. I take U1 to U2K plus 3, then I attach U2, U4, 2 pendant vertices only in U2, U4, U6, and U2K plus 2. Then I identify what is a equitable independent dominating set and independent set. The difference between these two is K. So like that, in some cases is less than, we construct a graph also. We give an example for this. IE of G strictly less than beta naught of G. In this graph, independent number is U2 and U4, 2, but equitable independent dominating set is U1. Okay, this is sufficient for dominating all the vertices, which is also equitable. This is another example. Okay, so now I come to the main topic, secure equitability in graphs. Secure domination is a well-studied concept. These are the references I will show you. In this domination, a vertex outside has the chance of coming inside the dominating set by replacing an element of the set without affecting the domination. So we have a property called domination. Based on the dominating property, we construct a set which is a dominating set. Now you take one vertex from outside and replacing a vertex inside. Still the set is a dominating set. Then that particular set is called secure dominating set. So once again repeat, each and every person outside has rights to get into the set, get into the committee. So once we replace one person from the committee, then the particular committee is called secure committee. So the same thing we do it in domination theory, which is called secure domination. So now I'm going to club these two ideas, the idea of equitability and secure dominating, which is called secure equitable dominating set, is introduced and studied. Other concepts like independence, rigidity, security, etc. are also studied in this section. Secure domination, equitability are combined to define secure equitable dominating set. You'll see later what is the matrix formulation of that particular set. So this is a formal definition of secure dominating set. Yes, dominating set D of G is called a secure dominating set of G if for every U in V minus D, there exists a V in D such that U and V are adjacent and you replace V by U is also a dominating set, then this set is called secure dominating set. Then we identify what is the minimum cardinality, what is the maximum cardinality. Based on this, we have notations gamma SEC of G and capital gamma SE of G. So now I combine these two things. Dominating set is an equitable dominating set is said to be secure equitable if it's satisfying this condition also. The degree difference is less than or equal to 1 along with this secure condition, secure dominating set condition, then that is called secure equitable dominating set. So generally, V of G, the total vertex set is a secure equitable dominating set. So we can find a minimum cardinality. Once we start with capital V of G, then we reduce it without violating the conditions of secure and equitability. Then secure equitable domination is superhereditary, which is nothing but once you impose another, you add one more vertex to secure equitable set, again is a secure equitable set. That is, suppose D is a secure equitable set, then you add one more vertex outside D, that is from V minus D, then D union U is also a secure equitable set. That is called superhereditary property. Then these are the notations for minimum and maximum cardinality of secure equitable domination number, gamma E sec E of G and capital gamma E secure of G. So these are the values of some standard graphs, standard networks, complete graph, totally complete disconnected graph, then star, path, and cycle. Other than that, complete bipartite graph, wheel, and double star, and Peterson graph. So these are the small remarks or theorems. When it is equal to 1, this value is 1 only in complete graph. In all other graphs, it should be greater than 1. So this is the proof of that particular theorem. Secure equitable domination number equal to 1 if and only if G is complete. Yes, a secure equitable dominating set in a graph is minimal if only if it is one minimal. What is my one minimal? If you remove one vertex, then the minimality condition fails. So based on that, we have Worth's theorem for secure equitable dominating set. If it is minimal, if and only if for any of these 4 conditions holds. That is, private neighbor is not equal to empty. There exists no vertex in S minus U which is equitably adjacent with U. There is a vertex V in V minus S such that U is the only vertex in S which is adjacent with V, and you replace U and V is an equitable dominating set. Either U is an isolate, or if for any W in S, W not equal to U is adjacent with U, then S minus W is not equitable dominating set. So these are the 4 conditions for minimality of secure equitable dominating set. So this is the proof of the theorem. I will not go through the proof. Okay. So once we define the minimality condition, then we talk about irredundant set based on secure equitability. So satisfying any of 4 conditions, one or more of the conditions 1 to 4, then S is called SC irredundant set. It's a hereditary property. It has a hereditary property. Then we construct a chain also. This is a maximal concept. Then these are the 2 values: minimum cardinality of maximal irredundant set and maximum cardinality of minimal irredundant set. So maximal irredundant set. So these are the 2 notations for small IE, IR, SE of G, and capital IR, SE of G. Then this is the obvious result. A minimal secure equitable dominating set of G is a maximal secure irredundant set of G. This is a proof of the theorem. Anyway, I will share the PPT. Just we go through it. Then this is a chain which we have discussed earlier in both domination and equitable domination. Then we defined the equitable independent secure set. So like that, what we have equitable independent set, which is satisfying hereditary property. Then these are the cardinalities of, these are the notations for minimum cardinality of maximal independent set and maximum cardinality of maximal independent set. So this is an example for any maximal equitable independent set need not be secure. So for example, you take this graph G. Here I take U2, U3, U4, and U6. Clearly, S is a maximal equitably independent set of G, but which is not secure. We cannot replace any of the vertices from the any one of the outside vertices. Since there exists no vertex in S, which can be a place for U5 by going out. So for example, if U2 leaves S, giving place to U5, then it is not an equitable independent set. Similarly, U3, U5, U6. So it is not secure, but this is maximal equitable independent set. This is the next remark. A maximal equitably independent set is a maximal equitable dominating set, but maximal secure equitable independent set need not be a secure dominating set. So this is the observation. This example proves the statement of this particular remark. Then the next remark, if you take a maximal secure equitable independent set, if for every V in V minus S, S union V is not equitably independent set, then S is an equitable dominating set, but need not be a secure equitable independent set of G. I take a maximal secure equitably independent set. Then if for every V in V minus S, to add S union V, which is not equitably independent, then is a equitable independent set, but not secure. This is a result of, this is a remark which is proves IR's SE of G less than or equal, strictly less than gamma E of SE of G. That is irredundant, secure irredundant equitable set, secure equitably irredundant set. The coordinate of that should be less than secure equitably dominating set. This is an example. This is called Hutch graph. So we have one more example. Here also IER secure of G less than gamma E secure of G. Okay. Now I extend the concept of independence in terms of coloring. I take a partition of vertex set is said to be secure, independent, and equitable partition of G if each VA is secure, independent, and equitable. This particular partition is briefly called SEI partition. Each singleton is a secure, independent, equitable set. So the partition set is guaranteed. If you put all the vertices of a graph as a singletons, definitely each singleton set is a secure, independent, and equitable set, because there is no need to compare with other vertex, because that is the only vertex in the set. So the partition set is guaranteed. Now we are going to minimize it. Then the cardinality of that particular set is, and that particular partition is denoted by chi C of G, which is called secure, independent, and equitable chromatic number. So like what we have in coloring, we extend the same, which is called secure, independent, equitable chromatic number, chi secure of G. This is a remark because we are going to use this for proving theorems. If we take two vertices which are independent and equitable, if U and V have a common neighbor, then U and V cannot belong to the same element of a SCI partition. So why? The reason is equitable independent, then the distance between these two vertices is equal to 2. Then the common neighbor cannot enter the element of the partition containing U and V with a replacement from that element. Right? Okay. These are the values of standard networks. What is the chromatic number value? SCI chromatic number value of some standard graphs. Then when it is equal to 1, only in totally disconnected graph. So like that we construct other theorems also. We can give an example for a connected graph. The difference between chromatic number and the SCI chromatic number is A in B, A less than or equal to B. You take any two positive integers, you can construct the graph whose chromatic number is A and chromatic SCI number equal to B. This is an example. You take a graph obtained from complete graph on A vertices by attaching B minus A pendant vertices at a single vertex of KA. Then whose chromatic number is A, chromatic SCI of G is B. So we can say that the difference between these two is large, arbitrarily large. This is an example. You take a complete graph on 4 vertices, then you attach 3 vertices with 1 vertex of the complete graph. Then the chromatic number is 4, secure chromatic number is 7. So the difference between these two is arbitrarily large. When they are equal, we have certain examples. Be a cycle with odd number of vertices and the order of G is divisible by 3, then they are equal. Similarly, if order is n of odd degree, odd number of vertices, and n is n modulo 0 mod 3, then whose chromatic number is 3 and a chi SE of G is also 3. They are equal. Then these are the other examples. We can construct a graph also. See this, and this example, the value is r plus 2, here 3. So you can find the difference between the r minus 1. We can construct a graph whose value is r also. Okay. A degree equitable K coloring of a part of G is a partition of V into subsets. Each is independent set and also a degree equitable. This is already existing in the literature. It is proved by Dharmalingam et al. This is denoted by chi d of G. Now we construct theorems based on these parameters. When chi SE of G is equal to chi DE of G. So like that, we extend other theorems. This is called very famous result. This is called Northos-Cotton type of results. The addition of these two or the product of these two. So we can express these values in terms of number of vertices in the graph and chi DE of G. This is degree equitable chromatic number. And in some cases, just less than or equal to k into n plus 1 also. This is a proof of the theorem. Similarly, the product of these two lies between these two. N and k squared, n plus 1 whole squared by 4. G bar is nothing but the complement of G. Then these are the other remarks based on the results. What is chi SE of Kn plus chi SE of Kn bar? So K1, K1 bar, etc. A subset is said to be secure equitable. So now we are talking about only secure equitable set. We don't bother about dominating concept, secure equitable set. When a subset is said to be secure equitable, you take many vertex V in V minus S. There is a vertex U in S such that you replacing U and V in S, which is equitable, then it's called secure equitable set. Which is hereditary. Then we talk about the cardinality of this particular set. Based on the cardinality, we have two classifications. One is capital S and small s. Capital S maximum, small s is minimum. So now we combined these two parameters and values of these two parameters in terms of standard graphs. Okay. So the bound of small SC sec of G and capital SC sec of G is lies between 1 to n. If it is n, capital S is 1 if only if the graph is equitable. If it is 1, if it has a vertex which is an equitable isolate. Similarly, small s is equal to 1 if it is equitable. Similarly, it has, so these are the theorems, remarks for the values of 1 and n. Then any subset is secure equitable if only if S is secure equitable in G bar. Therefore, the cardinality of these two terms are equal. If it is secure here, secure equitable, definitely it should be a secure equitable set in G bar also. Then we find the results based on this. C secure of G need not be equal to DE of G. DE of G is nothing but degree equitable set. This is secure equitable set. This is degree equitable set, which is introduced by Professor Arumugam. This is a maximum coordinate of degree equitable set. Then these two are not related. We cannot relate these two things. This is an example. This is a maximal secure equitable sets U5, U1, U4, U3, U4. So the values of the set is this is 2. Here the minimum is 1. Okay. The next definition, independent and equitable set. So without domination, we defined or introduced these concepts. A set is secure as well as independent, then it is called independent and equitable. Okay. So like that, we defined cardinality also. Then these are the values of some standard graphs. Then this is a theorem. You can see the similar theorem in chromatic number. Chi lies between n by beta naught less than or equal to n minus beta naught plus 1. Similarly, instead of beta naught, we have secure equitable independent set. N by beta SE of G. This side upper limit n minus beta SE of G plus 1. Then we define a new concept. A graph is said to be SEI of complete, SEI secure equitable independent complete if the chromatic number is equal to n. Secure equitable chromatic number equal to n, then the graph is said to be SEI complete. What does it mean? Only possibility for finding the partition, chromatic partition of that particular graph is put all the partition of all elements of the partition are singletons. Then the graph is said to be SEI complete. So then we characterize it for any two distinct vertices U and V in V of G, either the difference less than or equal to 2 or they are inequitable. That is, they are not satisfying the equitability condition. Then we put all the vertices as singletons. Then the partition contains n elements. Then the graph is the corresponding graph is called SCA complete. Then you have proof also. So if it is n, then we say it complete. These are the other examples. These are not complete but SCA complete, because K1n, Wn, Km, these are not complete graphs, but they are all SCA complete. Already they introduced one concept, is called degree equitable complete. If for any two vertices, the degree of is greater than or equal to 1, then we can connect these two theorems. Any DE complete graph is SCA complete, but the other way is not true. The example is Wn. It's not DE complete, but SCA complete. So these are the main observations of DE complete and SCA complete. Okay. Then these are some remarks based on the order. We construct SCA complete graphs of orders 2 to 5. So for order 2, order 3, order 4, and order 5. These are the only graphs for SCA complete with 2 to 4. We can extend this also, but we try to find up to 5. Okay. This is the last part, matrix formulation for secure equitable domination. So we construct the adjacency matrix in terms of equitability first. The equitability adjacency matrix AE is defined as 1 if they are adjacent as well as degree equitable, 0 otherwise. Definitely this satisfying the following properties: symmetric, AE of G equal to AE of G. The sum of the entries in the ith row is equal to equitable degree of ith vertex. These are some standard properties of adjacency matrix. Here we impose one more condition, degree equitability. So once we define the adjacency matrix, equitable adjacency matrix, then we find equitable closed neighborhood matrix, which is nothing but NE of G, which is equal to AE of G plus I of n. Here I of n is the identity matrix of order n, and 1 n bar denote column vector of all ones. So now we have a integer programming problem for gamma E of G. So it's denoted by minimum of this objective function, summation I equal to 1 to n xi, subject to the constraints NE of G multiply with column vector is greater than or equal to 1 n bar, and xi belongs to the set 0, 1. This is the third condition. For any xi equal to 0, I lies between 1 to n. There exists a xi, xj equal to 1, I not equal to j, such that the interchange of ith row and jth column in NE and interchange of xi and xj in this particular column results the resulting product being greater than or equal to 1n. Just we interchange xi and xj if possible, and which is satisfying the condition greater than or equal to 1n bar, then we can find the minimum value of that based on integer programming. So for example, you take this graph G equal to, there are 6 vertices U1 to U6. I construct what is adjacency, equitable adjacency matrix and closed equitable neighborhood matrix. Then I'm applying the condition of constraints, finding NE of G. Then I check whether, see this, once is greater than or equal to 1. At the end, therefore, U4 can be replaced U2, U6 can be replaced by U2. Therefore, U1, U2, U3, U5 is equal to secure equitable dominating set of G with minimum cardinality. So there are 1, 2, 3, 4. Because once you satisfying this condition greater than or equal to 1, then this xi forms the dominating set. Okay, this is an illustration of that. So this is another example. You take a path on 6 vertices, then you take any set D arbitrarily, then you verify it. What are the, see this here, this is not equal to, not greater than or equal to 1. So it's not a, is a secure equitable set, but less than or equal to 3. So exactly equal to 3. So this is the other way of finding the secure equitable dominating set through integer programming. So these are the references. Just we communicated this paper to the journal. So waiting for the review reports. Thank you. Any questions? Any questions? Now, is it audible? Hello? If you have any questions, please post it in the chat box.
Hello.
Still, yes, ma'am.
Hello.
Yeah, yes, ma'am. It's audible.
Hello.
Hello, ma'am. It's audible.
Hello.
Hello, ma'am. It's audible.
Hello.
Hello.
Any questions?
Yes. I have received a question. Sir, whether work related to domination parameters like total pad, etc., done with this concept? No. Still, the problem is open. You can extend the concept of secure and equitability concept based on total pad set. Yeah, there are many results you can produce. Sivagami. Thank you, ma'am. Any other questions?
Question. Any other questions? Thank you, sir. Thank you.
Thank you, ma'am.
Sir, the answer was not audible. Can you repeat, sir?
Yeah. Dr. Sivagami, ma'am. Yeah, your question
Yes.
is whether
Question is?
whether the work related to domination parameters like total pad, etc., done with this concept. No. Still, the problem is open. You can extend the concept of secure and equitable domination. Ma'am, is it audible?
Could you get?
Yeah, can you hear me? Hello?
Okay.
Ma'am, can you hear me?
Yeah. Any other questions? No questions. Okay. Thank you, sir. On behalf of the organizing committee, I am happy to thank our speaker, Dr. R. Sundareswaran, wholeheartedly for enlightening us with his interesting facts in the topic Secure Equitability in Graphs. It gave us deep insight into the topic and also revealed interesting facts. The presentations was well organized and explained well with basic concepts. I'm pretty sure the precious information and knowledge shared with us will definitely help us in exploring the concepts in future. Once again, thank you, sir.
Thank you, ma'am. Thank you so much.
Now we have two parallel paper presentation sessions. First one chaired by renowned Professor Dr. R. Sivaraman of our department, and another one chaired by Dr. S. Hariharan of our department. Following that, we have a technical session 2 at 12 noon in Zoom. Thank you.
1900